Welcome back to Material and Energy Balances. In this very special video, we'll start to bring things full circle in this semester by starting Chapter 10, which is on unsteady state material balances. Before we do that, I want to briefly revisit the general balance equation, which says that input plus generation minus output minus consumption equals accumulation. And we've been working with this equation for the entire semester. And up until now, for every problem that we've done, we've always said that accumulation is zero on the basis for steady state. Zero if the process is a steady state process. And when I first introduced this idea of a steady state process, I did so by saying that a steady process is one in which no process variables are varying with time. In other words, if I take a snapshot of a process at a certain time and I come back some time later, and I take another snapshot of the process, all process variables should be the same. This is very obviously not true for a majority of processes. And at one point, I think I said in the class that steady state is the platonic ideal for an industrial process because consistency is good for a lot of things, for having a consistent product, for making sure that things are working properly. But real life is just never that accommodating. Like steady state is very rarely attained, but that is always the goal, as I mentioned. So in my discussion of unsteady state material balances, I want to briefly differentiate the difference between regular fluctuations, which would fall under the realm of process control, and more structured unsteady state balances, such as batch reactions or startup and shutdown of equipment. So I want to jot some ideas down and kind of organize my thoughts. So quickly recapping, steady state means that no process variables are fluctuating or changing with time. And here process variables can mean pressure, temperature, composition, molar flow rate, mass flow rate, volumetric flow rate. Every single thing about that process is going to be constant. Even the level of liquid within a tank, if it's a tank that's being filled and emptied. If that tank starts filling up, then the hydrostatic pressure at the bottom of that tank would change, and that would mean that the process is not steady state. And most processes have steady state as the goal for the operation mode of that process. That's because there's less of a chance of things going wrong. So you can imagine if temperature is fluctuating in a chemical reaction, for instance, you have the chance for a runaway reaction to occur, and that would be very bad. A runaway reaction is when the increasing temperature in a chemical reaction makes it go faster, which makes, if it's an exothermic reaction, it starts giving off more heat, which makes the temperature rise further, and the feedback loop just keeps amplifying and amplifying until you have a runaway reaction. So that's one example of a way that things can go horribly wrong if a steady state is violated. Another example is more consistent products. So if your pressure and temperature are constant in a chemical reaction, the outlet composition will also be consistent, and that keeps things running a lot more smoothly. There's a future class you'll take in your senior year called Process Control, which handles mechanisms for regulating fluctuations in process variables. In that runaway reaction example that I just talked about, one example of a process control mechanism would be a thermometer or a thermocouple that measures the reaction temperature. And if the reaction temperature starts getting too warm, there's a process control mechanism which would then increase the flow rate of cooling water or something like that to bring the temperature back down. So once again, that's for a future class. You'll handle all that in your process control class. That is going to be outside the scope of material and energy balances. Rather, in this class, we'll focus on simpler deviations from steady state behavior. So perturbations, batch reactions, startup and shutdown, those types of things. The opposite of a steady state balance is called a transient balance. This is meaning something that is varying with time. And mathematically, the way we can express that through the general balance equation starts similarly to how we've been doing. So for a mass balance, for example, mass in plus the rate of mass generation minus the mass output minus the rate of mass consumption. And of course, mass can't be generated or consumed. Equals accumulation. This is for a mass balance. And because we haven't dealt with any accumulation terms that are non-zero, we've never had to fill in how you algebraically express the mass that is accumulating over time. The way you do that is with a derivative. So dm dt is the rate of change of mass in a particular process unit or vessel with respect to time. And as you can tell, when I write dm dt, the solution of an unsteady state or a transient balance is going to involve solving a differential equation, which, so I know that differential equations is a co-requisite course. And if some of you might have taken it a couple semesters ago, you may be rusty. So in the next video, I will cover just a brief recap and refresher of how to solve a differential equation. Just as a note, in differential equations, you probably learned many techniques for solving many different types of differential equations. In ECH 3023, the types of differential equations that we'll solve will be limited to mostly separable differential equations. I'll teach you some other numerical techniques as well, probably in the coming lectures. So again, next video, I'll do a recap of how to solve a differential equation in a separable differential equation.